Hi, so welcome to MathStat 341. This is lecture 18. And so what I want to do today is I want to finish what we started last time, which was going from the central limit theorem to Stirling's formula. And one of the reasons I want to do this is it shows the connectedness of mathematics. Whenever you see certain things, you should start to wonder, is there a reason why I'm seeing this number here? Does this remind me of anything? There's a wonderful website called the Online Encyclopedia of Integer Sequences. And in the online Encyclopedia of Integer Sequences, not surprisingly, you find sequences of integers. And if you happen to notice the first couple of values of something that you're interested in, you can feed that into the encyclopedia, and it will tell you all the places it knows where this arises. And it will give you formulas for them if it can. It will tell you references. Is an extremely valuable thing. So if you can notice some patterns, if you can notice some things, you have the ability to then do some search and get an idea of how you might go about proving it. When you see a factor of square root of 2 pi, you should be thinking geometry. And then since this is a stats class, you should also be thinking maybe the standard normal or some kind of normal distribution. Maybe there's some connections with Stirling and the Gaussian when I see the square root of 2 pi, or maybe it's just a fluke. And so just something to have in mind. We'll then talk about random walks, and we'll prove the central limit theorem in the very special case of a fair coin being independently tossed. I have not bothered to prepare this part of the lecture because it's boring, straightforward, going through the algebra. Doing it once is more than enough. And so just pay attention to make sure I don't make too many bad algebra mistakes. It's good to just see one brute force attempt so you get an appreciation of these other methods we're going to get to later. This is the painful situation of tossing a fair coin. Imagine how bad it's going to be in general. And this gives hopefully a motivation for why we're going to be looking at generating functions. Okay. And then the big items to take away from this is the power of Stirling's formula. So while we're going to start today by showing how Stirling falls from the central limit theorem, we're actually going to use Stirling's formula to prove the central limit theorem in the special case of tossing a fair coin. This would be, of course, a circular proof. So we have to have an independent way of proving Stirling's formula if we want to then use it to handle the case of tossing a fair coin. I really want to stress the ability of looking at special cases and trying to glean some information, some intuition from looking at that. You can be misled, of course. And sometimes looking at smaller, simpler cases, you might find a method that works for those cases but doesn't work in general. So be very careful about how much to draw from a special case. I'm a huge Mark Twain fan. One of my favorite quotes of his is, "A cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one." For each experience in life, only draw the lesson from it that you should. He phrased it much better than that, but this is the point. Be very careful about what you extrapolate from something like that. Okay. And then the last, as always, is trying to find a good route through the algebra. A lot of times we can just brute force a problem, but that's not going to be necessarily enlightening, and it may not generalize. Is there a better way of looking at things to see the relationships? Did we talk about Morley's theorem early in the semester, the triangle and trisecting? So I'm reading a biography of John Conway right now, and one of truly beautiful theorems going back thousands of years is if I give you any triangle and I trisect the angles, and again, this is not being drawn well, I apologize. You get 3 points of intersection, and those 3 points always determine what kind of triangle. What would you guess? The picture sucks. What would you guess the type of triangle is? Equilateral. And so I don't think the ancient Greeks had a proof of it. I have, I think, the worst proof possible. I made a bet with one of my friends in grad school that it was trivial. All you have to do is write down the coordinates of the points, calculate the coordinates of the points of intersection, show the squares of the lengths are equal. And he dared me not that I couldn't, but that I wouldn't do this before we graduated. And so I was allowed to use programs like Mathematica to simplify and expand out the equations. It's about 50 pages involving polynomials of degree 50, roughly, and just showing that all the coefficients match, therefore they must be the same length. The best variables I found was to use things like the tangent of 1/3 of the angles over here. Those were really good variables. Without loss of generality, you could make this point 0, 0. You can make this point 1, 0. There's some things you can do to simplify the algebra, but it's truly painful. At the end of the day, I have a proof of Morley's theorem. And so per the bet, he had to take me out for dinner not to exceed $12.50. If I lost, I had to take him out for ice cream. I took him out for ice cream anyway, just because he drilled home a wonderful lesson. Just because you can do a problem one way doesn't mean this is how you should do it. It's nice to know that there's a solution. Conway, the master he is, has the best proof for this theorem. He starts off with an equilateral triangle and reverse engineers and constructs the triangle you start with. Absolutely beautiful. So if you just go online and Google Morley's theorem and Conway, you will see the proof. All right, so let's talk about what we did last time and just put in a little bit of the details. We're looking at sums of Poisson random variables. So here, x1 through xn independent Poisson one random variables, and we'll let x be their sum, which we know is Poisson with parameter n. So this is nice. Poisson is a stable distribution. Sums of Poisson is Poisson. What does this mean? It means the probability that big X equals n is the parameter lambda to the n e to the minus lambda over n factorial, which is n to the n e to the minus lambda over n factorial. Oops, that lambda is an n. As lambda equals n for x. Now we know that it's converging by the central limit theorem to being normal. So by central limit theorem, x is approximately normal with mean n and variance n. And this is because we can just calculate, the expected value of x is just n times the expected value of x1 because they're all the same. And the variance of x is n times the variance of x1 because they're all the same. What's nice is when I'm giving this lecture, I have this moment of fear. Maybe I should have prepared a little bit more. Maybe I should have checked to see, is the variance n or n squared? Well, by just looking at this, I know the variance of x is going to be n times the variance of x1. And clearly the variance of x1 has no n dependence because it's just a Poisson with parameter 1. So if I know it's either n or n squared for the variance, this immediately allows me to correct it's got to be n. It can't be n squared. So it's nice to know this. So what does this mean? What is the probability that a normal random variable takes on the value n if the normal random variable has mean n and variance n? So what's the probability a normal random variable takes on the value n with mean n and variance n? You should be able to give this mean in your head without any calculation. I'm asking you the probability takes on a specific value. What is that probability? 0, right? The normal is continuous. So I shouldn't ask, what is the probability that my normal with mean n and variance n takes on the value n? I should ask, what's the probability I take on a value between n minus a half and n plus a half? That's what's going to correspond to the Poisson taking on the value n. So the probability x equals n is approximately the integral from n minus a half to n plus a half. And now I have a normal distribution with mean n and variance square root of n. I'm sorry, with variance n. So it's 1 over square root of 2 pi n e to the negative x minus n squared over 2n dx. Okay, well, if you look at this, what is the integrand approximately? What's the exponent x minus n squared over 2n as n goes from n minus a half to n plus a half? What's the exponent approximately? Well, let's evaluate the exponent when x equals n. When x equals n, what's the exponent? Zero, right? If it goes all the way up to n plus a half, we get a half squared over 2n. This is e to the negative 1 over 8n. If n is large, what is e to the negative 1 over 8n? It's basically e to the 0, which is still basically 1. So this integrand is essentially 1. Fluctuations of size e to the plus or minus 1 over 8n. And if you expand that out, then it's going to be 1 plus an error of size order 1 over n. So we're integrating a function that's approximately equal to 1 over square root of 2 pi n over an interval of length 1. So it's just 1 times the average value. So we get n to the n e to the minus n over n factorial is approximately 1 times 1 over square root of 2 pi n times 1, which implies n factorial is approximately n to the n e to the minus n square root of 2 pi n. And if we trust the convergence, we can even get that the error term is going to be of size, multiply this by 1 plus something of size 1 over n. So it's amazing, the implications we get from the central limit theorem right here. One of the reasons I wanted to do this is that we are estimating the probability that x equals n by a normal variable from n minus a half to n plus a half. It's how do we handle the issue of a discrete and a continuous. If I tried to just look at the continuous at one point, it would be foolish. So I have to look at the continuous over a small region. Okay. So the slides we've seen numerous times by now. The normal distribution with mean mu and variance sigma squared is just what we've seen. 1 over the square root of 2 pi sigma squared, e to the negative x minus mu squared over 2 sigma squared. And then the central limit theorem says if we take, I still have the extra cursor. If we take a bunch of independent, identically distributed random variables, and we look at their sum, and we divide by n, that's going to be the average. And the hope is the more observations you have, the closer the sample average is to the true average. So whenever you're doing things, you always want to compare apples to apples. And so what do I think x n bar should be? The bar means averaging. I think it should be close to the mean. And that's why when we look at this new variable z and the standardization, we're going to subtract off the mean, because that's what it should be about. Then the next question is, what should the fluctuations be? Well, because the x's are independent, the variance of x n bar is just going to be 1 over n squared times the variance of x1, because they're all the same, which is just sigma squared over n squared. I'm sorry, I made a mistake. It's 1 over n squared, not variance of x1. It's 1 over n squared times what? The variance of a sum is the sum of the variances. And if you multiply by a constant, the variance shifts by the constant squared. So the 1 over n squared comes from the 1 over n, comes from the n in the denominators. But I have n terms. So it should be n times the variance of x1, or the variance of x1 plus the variance of x2. There's an extra factor of n. And so this tells us that the variance of xn bar is sigma divided by square root of n. And now this tells you why Zn is such a natural quantity to study. I've got this random variable that I care about, this average value, this xn bar. What's the distribution of xn bar? How many of you have ever used a table of logarithms? Just me. A skill that is no longer needed. How many of you know about logarithms? That you can do logarithms in different bases. You really only need one base. There's something called the change of base formula that allows you to convert from one to another. But that means you have to do a little bit of extra work. So do you want to do the extra work, or do you want to have a couple of different tables of logarithms on you? It's sometimes easier just to have a couple of other tables. When I give you a probability distribution, if I shift the mean, I really haven't changed it that much. If I rescale things, I really haven't changed it that much. So in order to simplify comparisons, why not, whenever you give me a distribution, let me just adjust it to have mean 0, variance 1. I will not do this for the exams that you guys are taking. Right? But it wouldn't matter if I then converted those back to normal numbers. In order to simplify comparisons, let's just take our distribution and let's adjust it so it has mean 0 and variance 1. And now let's see what it looks like. As long as your mean and variance is finite, you can always do this calculation. So in some sense, if I give you any distribution with finite moments, without loss of generality, it has mean 0. Without loss of generality, it has variance 1. The first moment that starts to show you the shape of the distribution is the third moment. If the distribution is symmetric about 0, what's the third moment? So if you have an even distribution, f of x is f of negative x, what would be the third moment? So you'd be integrating, x cubed against, f of x dx. And let's say this is even. So if you integrate, so what kind of function is x cubed times an even function? Odd. And if you integrate an odd function about a symmetric interval, what do you get? 0. So all of the odd moments vanish. So if I give you a symmetric distribution, the third, the fourth, the third, the fifth, the seventh, all those moments will vanish. So when I'm trying to look at the shape of a distribution, without loss of generality, the mean is 0, the variance is 1, and then it's the third or the fourth moment that starts to give you information about what the true shape is. You don't have any understanding of the shape with just the first two moments. The remarkable fact about the central limit theorem is that all I really need is the first two moments. This becomes normally distributed. The shape of the distribution does not matter. Now, you might ask, where do the third, fourth, where do those higher moments come in? They come in and they impact the rate of convergence. How quickly does it become normally distributed? That's where the third moment comes into play. Or if it's symmetric, the fourth moment comes into play. And we will see that when we do the algebra later. But this is what makes the central limit theorem so remarkable. It only depends on the first two moments. And because I can always adjust any distribution with finite first two moments to have mean 0, variance 1, this is why it's such a universal result. This is why it's not, imagine you have a sum of independent identically distributed exponential random variables. And you would have the exponential central limit theorem. And then you might have the negative binomial central limit theorem. This is why we don't have all these different things to learn. We only have one thing to learn. And it's because we only care about the first two moments, and without loss of generality, we can always rescale. Okay, so we've seen this slide before. You're just reviewing what is the gamma function. It's the generalization of the factorial function. Okay, and so the big result is if n is a non-negative integer, gamma of n plus 1 is n factorial. And then Stirling's formula, which we just talked about earlier, is n factorial is about n to the n e to the minus n squared of 2 pi n. This means if you divide the left-hand side by the right-hand side, it's going to converge to 1. All right, here's a couple of plots and the Mathematica code of some Poisson random variables, I think. What do you seem to notice as the values get larger and larger and larger? Oh, so it's not Poisson, it's binomial, sorry. What do these curves seem to be converging to? Yeah, they seem to be converging to normal. And so again, I strongly urge you to write some code, do a bunch of different distributions, look at what's happening. Look at binomial, look at Poisson. What's nice about Poisson is you have an explicit formula. Binomial, we have an explicit formula for a binomial distribution. What's the probability you observe k? It's just n choose k, and then either p to the k, 1 minus p to the n minus k, if it's not a fair coin, or 1/2 to the n if it's a fair coin. And so you can actually just plot these and see. And the last one, I think, is a parameter of 100. And with 100, that's looking pretty close to a normal distribution. Can a binomial with n equals 100 be a normal distribution? Could it be perfectly normal? I can think of 2 or 3 reasons why it can't be perfectly normal. It can't take on negative values. So first, it's limited. And similarly, it can't take on values larger than n. So before somebody gives me that as a second one, that's covered by yours. There's another reason why it can't be perfectly normal. It's discrete. So it can't be perfectly normal. It could be really close, but it can't be perfectly normal. And so at some point, it becomes useful to quantify how close are you to a normal distribution. It's wonderful to know that it converges to a normal distribution. Have I gone far enough for it to converge? How many of you have taken a stat class? And have they given you the law of 30? That once you have about 30 observations, the central limit theorem kicks in. Have they given you any justification for that? No. Right? I can give you a distribution where 30 is not enough. You give me enough time, I can come up with a really terrible example that has really bad slow convergence. But for most distributions that are nice, 30 is pretty good. And by 30, things have normally settled down. A lot of things depend like 1 over n. And so once n is 30, you might be within maybe 3%. But for those of you who are computer scientists, it's not just the dependence on the parameter, it's the constant. And so if it's 100 over n, then n being 30 might not be enough. But if it's 1/2 times 1 over n, then n equals 30 should be really good. All right. So again, I told you I have not practiced this because I really don't want to do this at all, but we have to do it at least once. There's a couple of ways to do this. I have decided, I guess, to be fair. And by fair, I mean 2 things. One is my coin is fair. It has a 50% chance of being heads and a 50% chance of being tails. The second way to be fair is I'm assuming the values are 1 and -1. And we've talked about this. We don't want to say what's 3 heads plus 2 tails. We can't do something like that. So we always have our random variables take on real values. Why am I doing 1 and -1? I could also do 1 and 0. Yeah, with 1 and -1, we get mean 0. We don't have variance 1. So we could adjust things a little bit so that we have variance 1, but we haven't done that. But this way, it makes things a little bit simpler. We expect the action to be happening around 0. Okay. And so S2n is going to be the sum. What do we expect the variance of, say, x1 to be? Well, this is 1 minus the mean squared times the probability that x1 equals 1 plus -1 minus the mean squared times the probability x1 equals -1. What are those 2 probabilities? 1/2. And because the mean is 0, they're both 1. So it's 1 squared times the half plus 1 squared times the half. So it's just equal to 1. So actually, we do have variance 1. If you think about it, it's not surprising that we have variance 1. Here's -1. Here's +1. We put half of our mass here. We put the other half of the mass here. And the mean is right in the middle at 0. So how far are you? We've cooked it up so that the variance is 1. So again, this is another reason why this is a natural thing to look at. So we can look at the new variable Zn, which is going to be S2n over 2n minus its mean divided by the standard deviation. What's the standard deviation? Well, let's do things a little bit slowly. So one of the dangers in the subject is always, when do you normalize? And so maybe I'm not going to completely normalize today to try to keep the calculation a little bit simpler. What is the mean of S2n? Zero. And the variance of S2n is going to be 2n times the variance of x1 because they're all the same. So it's just going to be 2n. So I could standardize S2n and have something converging to the standard normal. Or I could say S2n should be converging to a normal. What should the mean of that normal be? 0. And what should the variance be? Whatever normal it's converging to, it has to have the same variance as S2n. What's the variance of S2n? 2n. So it would have to be converging to that. Or I could study S2n over 2n, so that would be the average, subtract off the mean, and then divide by the variance of S2n over 2n. And again, I can calculate that without too much trouble. Any thoughts as to why I'm looking at 2n for the number of tosses? I'm doing this way. My possible values for S2n will be 0, plus or minus 2, plus or minus 4, plus or minus 6. I'm going to get a centered about 0. If I did an odd number, it would still be centered, but now my values would be plus or minus 1, plus or minus 3, plus or minus 5. It doesn't make that much of a difference. But I know, for instance, if I am looking at an odd number of things, there's 0 probability of having an even number. And just some of the little algebra games we have to, play. Okay, so we want to try to calculate what does the distribution of S2n go to? What do you think the most common value of S2n is? 0. So let's calculate what's the probability S2n equals 0. So that's going to be, I have to have the same number of heads and tails. So it's going to be 2n choose n, 1/2 to the n, 1/2 to the n. More generally, I could calculate what's the probability that S2n equals 2k. So I have to choose 2k of them to be heads. Or do I choose k of them to be heads? Or is it something else? So let's think about what this should be. I want the number of heads minus the number of tails to equal 2k. Do we agree it has to be an even number? If k equals 0, then the number of heads and the number of tails is the same. We also know the number of heads plus the number of tails equals what? 2n. So we can just add the equations and we can get twice the number of heads is going to be 2n plus 2k. So the number of heads is n plus k. and the number of tails will be n minus k. And if you look at it, that makes sense. If I now add the number of heads and the number of tails like this, I'll get a plus 2k. So if I want to have 2k as my net number of heads, it's going to be 2n choose n plus k, and then 1 over 2 to the 2n. And now we want to study this for values of k. So there's a lot of good things in this problem. It's trying to figure out what is the right scale to study. What k must we study? And remember, the variance of S2n equals 2n. So the standard deviation of S2n is the square root of 2n. So I need to know, how big of a k do you think we should look at? If k is 10, do you think that's a small enough value of k that we need to worry about it? Do you expect there to be sizable probability when we have k equals 10? What's the average value of k? So what's the average value of k? K is the excess in the number of heads over tails. 0. And the standard deviation is of size what? So what do we say the standard deviation was of size? I don't care about the constant, I care about the n dependence. What's the n dependence for the standard deviation? Nope. You're close though. We showed the variance of S2n is of size 2n. The standard deviation is of size square root of 2n. So what do we expect the standard deviation of k to be? That should be of size square root of n. I don't care about the constant front. I just care that it's of size square root of n. So if you flip a fair coin 2n times, I expect on average there are no more heads than tails. But there could be a few more heads or there could be a few less heads. How much do I expect the fluctuations to be? I expect them to be on the order of square root of the number of tosses. So of size square root of n is the same as of size 2 square roots of n or square roots of 2n. I just care about the n dependence. So if k is of size n to the 1/4, is that pretty close to the average? Do we have to worry about k of size n to the 1/4? Is that close? Yeah. What about k of size n to the 3/4? What's the probability that, say, k in absolute value is greater than or equal to n to the 3/4? Does anybody know what theorem might be useful? So Markov requires a non-negative, which we could use because I'm talking about absolute value of k. But I'm sorry? Chebyshev. So we could write this as greater than or equal to n to the 1/4 times n to the 1/2. Because we know the standard deviation is of size n to the 1/2. So fluctuations should be bounded by 1 over the square of the number of standard deviations. So this is going to be less than or equal to some constant divided by n to the 1/4 squared. And the reason I have to say constant is because I'm not calculating the exact value of the standard deviation. I'm not worrying about, is it the square root of 2n? Is it 2 square roots of n? I don't give a shit. There's so many places I'm going to make an algebra mistake. I don't even want to try that. I just know it depends on order and order square root of n. So if I have something of size n to the 3/4, that's n to the 1/4 standard deviations. Think of n as a huge number. Even Chebyshev, which is pretty weak, is enough to tell you the probability is damn unlikely. Yeah, this is going to give you something over n to the 1/2. If n is 10 to the 100, that's still 10 to the 50. Huge, huge denominator. Insignificant probability. So really, it's enough to study, let's say, the absolute value of k less than or equal to the log of n times the square root of n. Because if k is as large as the log of n times the square root of n, we've already gone log n standard deviations. That's 1 over log square root of n by Chebyshev. That's enough to go to 0. Or we could do n to the 1/2 plus epsilon. That would give us a 1 over n to the 2 epsilon, and again, it would be small. So the idea is to get a sense of what scale do we want to study things. If k is very, very large, Stirling's formula will suck when I try to expand things. If k is very, very small, we'll be in great shape. So we have 2n, choose n plus k, 1 over 2 to the 2n. The 1 over 2 to the 2n, I understand that. What can we do to the 2n, choose n plus k? How can we write that? Expand it. So this is going to be 2n factorial over n plus k factorial, n minus k factorial, 1 over 2 to the 2n. How should I approximate the factorials? So what should I use to approximate the factorials? Stirling, right? Foreshadowing. We did several things with Stirling at the start of today. Now, if I want to use Stirling, what should be true about the number that I'm applying it to? It should be what kind of number? Large. I'm not going to use Stirling's formula to estimate 1 factorial or 2 factorial. Although, as an aside, it might be interesting to go and see how well does Stirling do for 3 factorial. I want these numbers to be large. So, want large for Stirling. So need 2n, n plus k, n minus k large. Okay, of these quantities, one of them is clearly going to be large, the 2n. I'm not worried about that. Is it possible for n plus k and n minus k to both be small numbers? No, at least one of them is going to be large. That's good. But it is possible that one of them could be small. Could you give me a value of k that makes something small? So for what values of k could things be small? N, and the other value, negative n. So need k bounded away from plus or minus n. This is why we showed enough to study the absolute value of k at most, say, log n times n to the 1/2 or n to the 1/2 plus epsilon. The work we did there is enough to show that we don't have to worry. Okay. We didn't need a great bound. If n is large, even if k is of size n to the 9/10, that's going to still be your n minus n to the 9/10 is still approximately n, right? The danger from that is really small. So whenever you're doing calculations in math, it's always good to get a sense of how clever do you have to be. Do we have to be extremely clever? Do we have to be moderately clever? And for what we're doing here, we don't have to be that clever. Is it worth being more clever? When you proved the I'm going to pretend you actually proved the fundamental theorem of calculus in one of your classes, okay? So when you proved the fundamental theorem of calculus in one of your classes, I'm sure they talked about convergence. No. So yeah, you get the upper sums, you get the lower sums, they converge. We don't really care about the rate of convergence because all we care about is the result in the limit. And in the limit, you have the area under the curve is the antiderivative at b minus the antiderivative at a. We don't care about how quickly it's converging. Now, if you're applying this to the real world and you're trying to estimate an integral, now you care about the convergence rate. So if we actually care about how close is the Gaussian to the distribution of the sample mean, then we care about the rate of convergence. If we're only caring about what's going on in the limit, we can be looser. We don't have to worry about things as much. And so over here, I don't need anything too good. Log n into the 1/2, n to the 1/2 plus epsilon. I could even probably do n to the 9/10 would be more than enough. The probability is going to be dropping off so fast, it doesn't really matter. So now we want to expand these using Stirling's formula. So before we do anything, let's just restate Stirling. So Stirling is n factorial is about n to the n, e to the minus n, square root of 2 pi n. And so we have n plus k factorial, n minus k factorial, 2n factorial, and a 1 over 2 to the 2n. All right. So the n plus k factorial by Stirling is going to be n plus k to the n plus k, e to the minus n plus k, square root of 2 pi n plus k. And then the next one is going to be, just going to erase. I'm afraid I'm not going to have enough room, so let me just move this over. Okay. And then for the n minus k, we're going to get n minus k to the n minus k, e to the minus n minus k, square root of 2 pi n minus k. All right, I'll put the 2 to the 2n in the numerator. Now I have to expand 2n factorial. That'll be 2n to the 2n, e to the negative 2n, square root of 2 pi times 2n. And now it's time to just do some algebraic simplifications. So we have 2 to the 2n, n to the 2n, e to the negative 2n, square root of 2 pi times 2n. And then we have 2 to the negative 2n. Downstairs, I've got n plus k to the n plus k, n minus k to the n minus k. I've got an e to the negative n plus k and an e to the negative n minus k. So the k terms cancel, and we'll get an e to the negative 2n. We'll get a square root of 2 pi times 2 pi times n minus k times n plus k. Okay? And now we see a lot of cancellation. The 2 to the 2n cancels with the 2 to the 2n. The e to the negative 2n cancels with the e to the negative 2n. 1 factor of square root of 2 pi cancels with a factor of square root of 2 pi. I've got a 2n. I'll keep it like this for now. And so now, what am I left with? There's a couple of ways of doing the resulting algebra. And so let's just collect things first. So I've got the square root of 2 pi, oh, it's not 2 pi, 2n, divided by 2 pi n minus k n plus k. And then I have an n to the 2n over n plus k to the n plus k, n minus k to the n minus k. As n gets really, really large, what does the first factor go to? It does go to 0, but let's look at its independence. So we'll have a square root of 2 over 2 pi, and then we have n over n minus k, n plus k. But we know k isn't that large. So what is n minus k times n plus k? It's approximately n squared. N over n squared is 1 over n. So it's looking something like this. Okay. What did we do you remember what the variance is of S2n? 2n. We don't have a 2n here. I could write this if I wanted to as the square root of 2 times 2 over 2 pi times 2n, which is then twice over the square root of 2 pi times 2n. And now if you look at that, the 2 pi looks like the 2 pi from the Gaussian. The 2n looks like the variance. There is this factor of 2. And the factor of 2 is coming from the fact that if we want to take a value of 2k, say 2k is 4, and the next value is 6. So my interval for 4, where should it go from? What interval covers 4? 3 to 5. Before we did it n minus a half to n plus a half, and that was an interval of length 1. But now if we want to do something like 4, we have to go from 3 to 5. That's where that 2 is going to come from. So far, everything we're doing here, that looks pretty good. All right? So now let's look at the other term. So there's a couple of ways to analyze this. One thing I could do is I could pull out the n to the 2n and notice, hey, look, every factor has an n to it, right? If I pull out an n from the first factor to the denominator, I get n plus k times. If I pull out from the second factor, I get it n minus k times. I have n to the 2n upstairs. So this is the same as 1 over 1 plus k over n to the n plus k, 1 minus k over n to the n plus k. I'm sorry, to the n minus k. I'm just taking the powers of n and moving them into the denominator. So, k is less than or equal to, either log n times n to the 1/2 or n to the 1/2 plus epsilon with high probability. As n goes to infinity, what do you think 1 plus k over n to the n plus k goes to? I'm sorry? We want to do a little bit better than that, maybe. Does this look like anything before? 1 plus x over n to the n? Yeah, doesn't this look like e to the k? And the other one looks like e to the minus k. So the product is converging to 1. Unfortunately, if that were true, then when we go back a page, we would have something converging to a uniform distribution, not a normal. So the problem is we were too crude here. K is small relative to n, but it's still potentially a big number. And so if we didn't have the plus k, then yes, 1 plus k over n would converge to e to the k. 1 minus k over n would converge to e to the minus k. But when I look at the extra plus k and minus k, those could have some secondary effects. So we have to be a little bit more careful in how we deal with this. So for some things, it's okay to say k is very small. And the reason we could do it before is if we go back a slide, when we looked at the denominator, we only had two terms in the product, an n minus k and an n plus k. So because the number of terms we had was bounded independent of n, it didn't really matter. But over here now, we are raising things to the n plus k and the n minus k. Now that extra plus k makes a huge difference because it's growing with n. If I'm off by just a little bit, if I only do it 3 or 4 times, I'm still off by just a little bit. But if I do it a tremendous number of times, it's now huge. And that's the problem. So we have to be a little bit too crude. I'm sorry, we have been too crude. We can't be that crude. So we have to analyze these products. What should you do to analyze these products? Logarithms, right? This is the Pavlovian response from taking a class with Miller. So Pavlovian response, take log if C product. Okay. So we have, let's let fancy P equal 1 plus k over n to the n plus k times 1 minus k over n to the n minus k. So the log of fancy P is going to be n plus k, the log of 1 plus k over n, plus n minus k, the log of 1 minus k over n. And recall the log of 1 plus or minus u is minus u plus or minus u squared over 2 minus u cubed over 3 dot 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 dot. Oh, sorry. Sorry. I'm going to get it wrong if I try to do too many steps at once. So let me just do it slowly. Let me say the two ones. The log of 1 minus u is negative u minus u squared over 2 minus u cubed over 3 dot dot dot. The log of 1 plus u is u minus u squared over 2 plus u cubed over 3 dot dot dot. And again, you can check, once you have one of them, replace u with negative u, and you should get the other. What's the log of 1? 0. The log of 1 minus u, if u is a small positive number, should the log of 1 minus u be positive or negative? So if u is a positive number, should the log of 1 minus u be less than 0 or greater than 0? It should be negative. And so you see that the top does make sense. If u is a small positive number, if u small and positive, the log of 1 minus u is negative, and the log of 1 plus u is positive. So this is not a proof that I've got the correct Taylor series, but they're at least starting off correctly. And again, if you can ever do simple checks to see if you're on the right track, do it. And so this quickly shows that everything is looking quite reasonable. So now we can expand things. Now, when I'm expanding things, I really don't want to use infinitely many terms. So the question is, how many terms do I need to keep? Well, we know k is roughly of size log n, roughly of size square root of n. So when I look at k over n, think of that as worst case scenario that's maybe 1 over square root of n, maybe a little bit larger than that. If I square that, that's going to be something of size maybe roughly 1 over n. I'm multiplying by n plus k. if I'm multiplying something that's of size 1 over n by something of size n, that product could contribute. But once I get to the cubic term, if k over n is roughly of size 1 over square root of n, then when I cube it, it's going to be size roughly 1 over n to the 3/2. When I multiply by something of size n, that's going to be something of size 1 over square root of n. It's going to be insignificant. So as the absolute value of k is less than or equal to log n times n to the 1/2 or n to the 1/2 plus epsilon, only need quadratic. We don't need to worry about the cubic terms because they're going to be insignificant. A lot of the proof we're doing here is going to follow similarly for general distribution. The analysis is simplified by the fact that we are using just a coin toss. But the general proof strategy will be very similar. It'll just be a little bit more involved. Okay, so now let's analyze. So the log of P is going to be n plus k, and now we expand the first part. So we're going to get k over n minus k squared over 2n squared plus much smaller. And then the next piece is going to be plus n minus k. And then we're going to start off with a minus k over n minus k squared over 2n squared plus dot, dot, dot. Okay. So now let's start looking at things. So the first is I have the n times k over n and the n times negative k over n. Do those contribute? Or do they perfectly cancel? Those cancel, right? One has a plus sign, one has a minus sign. So we don't have to worry about those. Good. Let's look at the next one. We now have n times negative k squared over 2n squared. We have n times negative k squared over 2n squared. Do those cancel or reinforce? What happens here? Cancel or reinforce? Reinforce. And so now we're going to get minus k squared over n squared, because we have two of them, times an n, so it just becomes minus k squared over n. And if you think about it, if k is roughly of size square root of n, this is something that could contribute. And now that handles all of the n terms. Now we have to handle the k terms. Okay. So now we have the k times k over n and the negative k times negative k over n. Do those cancel or reinforce? Reinforce. And so now that's going to give us a plus k squared over n, which is going to perfectly balance out with what we just had a moment ago. And now, oops. I'm a little worried here. Did I? All right, so now for the next terms, do they cancel or reinforce? So they cancel. And so there is an algebra error here because everything should cancel. We're off by a factor of 2 somewhere. So I'm trying to see if I can quickly see where the error is. N plus k log. minus k squared over 2. All right, all right, we're off by a factor of 2. So let me quickly try to go back and see if we can find where the mistake is. So we definitely want n plus k, we want n minus k. We have 2 to the n. N plus k, n minus k. No, that's all right over here. And so now take logs.
On the orange term, should there be 2 in the denominator still?
It would be lovely if that were the case. Oh, wait a minute. Right, and we have 2 of them, right?
Oh, yeah.
So it should be twice that. That's where the factor of 2 is. It should be negative 2 times that. Good, thank you. So that fixes things and we're left with negative k squared over n. Okay, now I've taught this class numerous times. I've given this lecture numerous times. There's always some algebra mistake, which is why I told you I want to do as little algebra as possible. I knew something would happen. I don't want to write it as k squared. I want to count. It's not k that I'm going to get. It's twice k. So I really want to write this as 2k divided by 2 squared over n. So this becomes the same as negative 2k squared, and then down below we're going to have a 4n, or negative 2k squared over 2 times 2n, or negative 2k minus 0 squared divided by 2 times 2n. So I'm trying to impress you with my algebra skills because I just screwed up earlier. I got to redeem myself. Why the hell would I write it as 2k minus 0 squared over 2 times 2n? It looks like the Gaussian. Which Gaussian? There's more than one Gaussian. I went to the Ohio State, there's one. But which Gaussian does it look like? Not the standard. Which 2 parameters do you have to give me to tell me which Gaussian you have? You have to give me the mean and the variance. 2k minus 0, that's looking like something with a mean of 0. And the denominator is now written as 2 times 2n. It's looking like something with variance 2n, because the denominator is 2 times sigma squared. So now that's the log of p. Thus, p is approximately e to the negative 2k minus 0 squared over 2 times 2n. So the probability that S2n equals 2k, our constant was 2 over the square root of 2 pi times 2n, e to the negative 2k minus 0 squared over 2 times 2n. This is almost a Gaussian with mean 0 and variance 2n. The issue is we have this factor of 2. And this factor of 2 is because we're integrating from 2k minus 1 to 2k plus 1 of the normal density mean 0, variance 2n. And that's where that extra factor of 2 comes from. Because we're not calculating the probability we take on the value of 2k plus or minus a half. It's 2k plus or minus 1. So there's a lot of good subtleties for this problem. But at the end of the day, when the dust clears from Stirling's formula, we got the central limit there. One bad algebra mistake was recovered without too much time. And this is the special case of tossing a fair coin. The best way to appreciate a theorem is to do a painful calculation. So go home and try to redo the calculation where the probability is, say, 3/4 for a head, or more generally, P for a head. See if you can do it. And you might find, it really wasn't that bad. I just changed the 2 to the 2n to P to the n minus. So if we try to generalize, now, probability P of heads, the 2 to the 2n is going to become a P to the n plus k, and then a 1 minus P to the n minus k. And I guess this would be a 1 over. It'd be 1 over 2 to the 2n. It would become P to the n plus k. And if P equals 1/2, you can see that they're the same. But this is now going to give you some additional factors to play with that you're going to have to work with. You should probably be able to still do it by a more painful route along these lines. But I encourage you to just see for yourself, what would it be like to try to extend this argument to just a general weighted coin? And if we're having this much trouble with coins that only take on 2 values, what's it going to be like when we try to do sums of all these other random variables? I'm trying to really motivate why we're going to be spending time on generating functions. The best motivation is to just see how painful the calculations are. So what are generating functions? So if I give you some sequence an, we define its generating function by the sum an s to the n. And we look for all s where this converges. And then this should hopefully remind you of the calculus you did in high school or Math 150 here, when we talked about sequences and series and when they converge. So in some classes, you can get into trouble for being a smartass. In this class, you get extra credit. Do not answer unless you are willing to be a smartass. What is the simplest sequence of an we can study? Where we can understand that sum. Simplest sequence. 0, right? If we take an equals 0 for all n, this yields g, I'll call it 0 of s, is just 0. That is really easy to study. Converges for all s. Okay, can you give me another sequence that's somewhat easy? An equals 1, the next simplest. And that yields, I'll call it g1 of s, is now the sum and goes from 0 to infinity of s to the n. Have we seen this before? Yeah, what series is this? Geometric. So this is just 1 over 1 minus s if the absolute value of s is less than 1. If I take an equals 1 over n factorial, we get g, I'll call it factorial of s, is just e to the s. And that converges for all s. It turns out that for a lot of sequences, we can get a closed form expression for the g's. And if we have a closed form expression for the g's, we can often use that to get information about the coefficients. But what's really nice is hope. If I give you some sequence GA of s and another sequence GB of s, this should be some sequence which is a function of a and b of s. That if we take 2 sequences and combine them, and maybe it's not multiplication, maybe it's something else. Or maybe FAB is maybe addition over here. And maybe the generating function converts addition to multiplication. If I give you a sequence A and a sequence B, should there be a nice formula for g of A plus B? Well, that should just be the sum. So if I just add two sequences, it doesn't seem like the generating function is going to be particularly nice if I'm just adding them, coefficient by coefficient. But maybe there's other ways to combine things. So let me quickly go through the Fibonacci numbers. So the Fibonacci numbers are defined by, we start 0, 1, 1, 2, 3, 5. Each number is the sum of the previous two. There's a beautiful formula called Benet's formula, which gives an explicit expression for the nth Fibonacci number. So you can jump to the nth Fibonacci number. Here's how to analyze them using generating functions. Let's define g of x to be the sum of fn x to the n. At first, you might be thinking, does this make any sense to do? If I knew the Fibonacci numbers, why would I be writing down the generating function? Well, we know the Fibonacci numbers. Once I give you the recurrence relation and the initial conditions, I can just rattle off numbers. The numbers are going to just be, 0, 1, 1, 2, 3, 5, 8, ... But it might be hard to extract what they are. I can't just tell you what the 100th Fibonacci number is without calculating all the stuff beforehand. Benet's formula allows me to jump to anywhere I want. How many of you have taken differential equations? If you were to take differential equations, one of the techniques you should see is the series solution method, where you guess that the solution to a differential equation is a series, and then you get some relations among the coefficients by taking derivatives. So if I look at fn plus 1, xn plus 1, if I just start looking at this sum, I can use the Fibonacci relationship to write fn plus 1 as fn plus fn minus 1. I will now, how can I extract something from that? Well, over here, when you look at fn x to the n plus 1, that's almost fn x to the n. So why don't I just pull out a factor of x? And that's what's happening over here. We're pulling out a factor of x, and now we just have fn x to the n. And over here, we have n minus 1 and n plus 1, so I want to pull out two factors of x. And so when you go through and you do the algebra, you now get a line like this, where each term is almost the generating function. They're just missing a few terms in the beginning. And this is where you do one of the two things you can do in mathematics. What are the two things you can do in math? You've got to learn the two ways to do nothing. Add 0 and multiply by 1. This is an add 0. We want the sums to start at 1. So just add the terms you need so the sums start at 1 and then subtract. And so when you do that, we now have to subtract a few terms here. We have to subtract one term here. And we're left with now g of x on both sides. So we have g of x, g of x, g of x. Just solve for g of x. And when the dust settles, you get g of x is x over 1 minus x squared. We have an explicit closed form expression for the generating function. All right. We could try to expand this by using the geometric series by taking r equals x plus x squared, but that would be really bad because you would have things coming of different degrees. And so it's much better to factor the denominator and use that least favored method from calculus, partial fractions. There is a use for that. So we factor the denominator and we do a partial fraction expansion. And now that it's a partial fraction expansion, we can use the geometric series for each one of these. And then when you expand it out and the dust settles, you get Benet's formula. So this should hopefully be a good motivation for why we might care about generating functions. We start off with a relationship. We build this function, and because we have an explicit formula for the sum, we can use that to deduce information about the coefficients. What we're going to do on Thursday is we're going to apply this to probability. The sequences we choose will be the probabilities of events. And then we'll somehow combine a bunch of random variables and have a new generating function that will be the probability of the sum of the random variables. And we'll get a closed form expression. And what do you think that closed form expression is going to converge to the generating function of? The Gaussian. All right, so that's a good place to stop for today.